Welcome back to another video, and this video is mainly about what is a derivative. Now, last video we talked about how to evaluate limits and what limits necessarily mean. And this time we're going to be talking about how we can count that change over time, right? Or the variable change that we have. So there are two different key concepts that we have today. We have average rate of change and instantaneous rate of change. Now, we all know what an average rate of change is. It's just the average, how much it changes over time, divided by how much time there is, right? So let's write that down as an example. Let's say we have this graph of 2x, right? Let's say we have this graph right there, right? And the way how we would find the average rate of change is just by taking 2 points, right? And then we're gonna make the delta y over delta x, right? That's gonna be necessarily our slope, basically. So let's say we have points of -5, comma, -6, and we have 3, comma, 4, right? Now, the whole reason how we would find the average rate of change is by using these points, right? We have delta y over delta x. The triangles means delta. And that's just equal to y2 minus y1 over x2 minus x1, right? That's how we're going to find the average rate of change. So once we plug all those coordinates in, we have -6 minus 4 over -5 minus 3. That's going to be equal to -10 over -8. And of course, the slope equals 5 over 4, right? But what can we actually tell about this line if it was in a quadratic, right? So now when we have a quadratic, it's going to be like x squared plus something, right? And if we draw it out, we have this. That's something that we can have. In this case, this function has 0 roots, right? Because it doesn't touch the x-axis. But let's name it f of x, right? Now, let's say that f of x is equal to x squared plus 1, right? There is no actual roots here, it's just imaginary. So in this case, to evaluate for the the average rate of change, right? We're gonna have to use a few points. We're gonna do points at x equals, let's say 5, and at points x equals 1, right? So now, if we do a zoom up of it, right, we got x equals 1 right there. We're gonna use a different color, right? We got x equals 1 over here, and then we got x equals 5 over here. Now, if we draw a line here, you see how it touches the function, and then it untouches, and it touches it again. This is what we call a secant line, okay? This is what we call a secant line. Now, the whole reason why we do have a secant line is because a secant line is a line that touches 2 points, well, 2 or more points, but it never touches at 1 point, okay? So by evaluating this limit, delta y over delta x, right? Oh, I keep on saying limit. By evaluating the average rate of change, we have delta y over delta x, and that's just equal to f of 5 minus f of 1 over 5 minus 1. Now, how we're going to evaluate this, f of 5 is equal to 26 in this case. 26. F of 1 is equal to 2. and over 5 minus 1 equals just 4. That is equal to 26 minus 2 equals 24. So we have 24 over 4, and our average rate of change equals 6. So now we're wondering, since the average rate of change necessarily just means the secant line of a function, what does it mean by the instantaneous rate of change? Now, in this case, the instantaneous rate of change is something else, right? And by referring back to the secant line where it's the average, this time we have the instantaneous. So something tells us that we need to find the tangent line. All right, here we're gonna write down our tangent line. You might say that it's nearly impossible for us to figure out, oh, what is the tangent line of a function, right? But we have a really simple way of doing it. Well, it's not really simple, but it's good enough to those who we know the basics of. And let's say you have the graph of like y equals x, right? This is y equals x. Y equals x. Now, that's really simple to find the tangent line of because the slope is the same on all points, right? So we know that the tangent line is equal to 1 because of the slope equals to 1, right? And the thing is, what if it was in a quadratic? That complicates a few things, right? Primarily, we're going to be using the whole entire scenario of y equals x squared, just because it's more traditional to me, and it's a lot easier to explain a lot of things. So, let's say we have y equals x squared, right? I draw my best graph here. There we go. Y equals x squared. How can we actually find the instantaneous rate of change, right? So this is where limits come in. Remember how we did evaluating limits and everything else? In this case, we can use something called the difference quotient. Now, you might ask me, what is the difference quotient, right? It's something that you haven't heard of, and I'm here to tell you. Okay, so this is what we have as a difference quotient. Difference quotient. Okay. So our difference quotient states, I'm gonna move this down a little bit. Our difference quotient basically just tells us, okay, how we're gonna find the instantaneous rate of change. Because let's say you have a graph, right? And we're gonna refer to the graph on the top. And our secant line is from this point to this point, right? And we want to find the instantaneous rate of change of this magical point. So now how we're going to do this is we're going to be basically moving the upper bound more towards the inner bound. More towards the point that we need to find. And we're going to move the bottom bound to the point that we need to find. In this case, it sounds a lot like limits because you're trying to get arbitrarily close to a value by just evaluating for it without even, trying to, because it's going to be infinite points, right? You can have, if it was like x equals 4, then you could have x equals 4.001, right? And it's not nearly as close as you think it is, but it is, right? So now, back to difference quotient. After understanding that whole entire process, the difference quotient states that it helps you move the point arbitrarily close to a value that you're trying to evaluate for. The difference quotient is the limit as h approaches 0, right, of f of x plus h minus f of x, everything over h. Now, by looking at this equation, you're going to be like, oh, it's just going to turn out to be undefined because the denominator has 0 in it. But you're going to have to wait and see because we have f of x plus h, and in most cases, the h cancels out, right? So that's our difference quotient. Now, the whole point that we're going to be using is, let's say the function was f of x equals x squared, right? So now, just because it's x squared, right, we can find the instantaneous rate of change at a certain point, right? Now, we still have to turn that function into a function where we can find the slope of everything, right? And that would be just what we call the derivative, right? So we're going to find what equation that it uses for all slope points, right? So the derivative of a quadratic is just a linear function. And of course, the derivative of a linear function is just the horizontal line based off of like, oh, what your slope is, right? So let's start evaluating for it. We have the limit as h approaching 0 of f of x plus h minus f of x over h. That's equal to the limit as h approaching 0 of x plus h, and then put that all in parentheses squared, minus x squared over h. Okay, now it doesn't look too bad. For our x plus h parentheses squared, we can use a binomial theorem, which is also Pascal's triangle, but since this is in a really small case of the highest exponent of 2, we don't really have to use it. So that'll just be equal to the limit as h approaching 0 of x squared plus 2xh plus h squared minus x squared, of course, all over h. Now, we can see a few terms that we can cancel out. We have a positive x squared and a negative x squared, so those we can cross out. And then we have h as a denominator, right? But we can use a certain way to factor it out, right? So h, 2xh over h is just 2x, right? So we're going to cross that out. And then h squared over h is just h. Cross that out and make it to h. And of course, the denominator also cancels out because we just used up all of the denominators, right? And that is going to eventually lead us to equals to the limit as h approaching 0 of 2x plus h. And by plugging in h as 0, we find that our derivative, or our instantaneous rate of change function, for all points is 2x. So now you're asking me, how can we find the instantaneous rate of change of a value, right? So now in that case, well, the value, right, that we're trying to find, right, is whatever value, like x equals, let's say 4, right? X equals 4. Let's say we want to find the instantaneous rate of change for this. And usually we call it IROC for instantaneous rate of change, right? So let's see. We're going to be using this function, right, as f of x equals x squared. We're going to find the relationship between these. So how we're going to evaluate this is that the limit, we're going to use the difference quotient, right? The limit as h approaching 0 of f of x plus h minus f of x over h. Now, since we know what x is, we can plug in x, right? So the limit as h approaching 0 of f of, it was 4 plus h minus f of 4 over h, right? So now, that ultimately leads us to the limit as h approaching 0. Move this down a bit. Of 4 plus h squared minus, well, since f of x equals x squared, so that means that f of 4 is equal to 16 because 4 squared equals 16, right? Over h. And of course, that's going to lead us to the limit as h approaching 0 of 16 plus 8h plus h squared minus 16 over h. Now we're going to do the same thing that we did before with all of the canceling out. 16 and the negative 16, they cancel out. The h cancels out and it becomes 1h, right? So now, once we finish evaluating this limit, the limit as h approaching 0 of 8h plus h, right? And, I mean, not 8h, should be 8 plus h, right? And once we substitute into 0, we get the instantaneous rate of change as x equals 4 is equal to 8. Now, how can we look at it a different way? So first off, the limit that we previously evaluated, it was 2x, right? Since x equals 4, and if we even plug it into the rate of change function that we have, it's still going to be equal to 8, right? So that's the relationship between these two functions, right? Where the way how we find the derivative of a function is just by doing the limit quotient, right? But then if we're trying to find the derivative of a function at a singular point, we use the difference quotient, but we also substitute in the x before we evaluate the whole thing, okay? So as an example, try this. Find the instant rate of change of, let's say, x squared of, well, the function f of x equals x squared minus 5 at x equals 2. So try this as a practice. Find the instantaneous rate of change of f of x equals x squared minus 5 at x equals 2. So now you can pause the video here and try to evaluate it, and we'll get right back to it. Okay, so assuming that you guys just evaluated for the difference quotient and everything else, we found the instantaneous rate of change, right? We're going to try evaluating this now. So by listing what we know, f of x equals x squared minus 5, x equals 2, right? So now, by using the difference quotient, the limit as h approaching 0 of f of x plus h minus f of x over h is just equal to the limit as h approaching 0 of f of 2 plus h minus f of 2 over h, of course. And by evaluating for that, right, we get the limit as h approaching 0 of x squared, well, not x squared, 2 plus h, that parenthesis squared, minus 5, and then minus f of 2 in this case would be 2 squared minus 5. 4 minus 5 equals negative 1. So minus a negative 1. We have a lot of signs here, so we're going to have to cancel those out too. So double negative makes a positive, right? Just for the ease of things. That evaluates to the limit as h approaching 0 of 4 plus 4h plus h squared minus 5 plus 1. Now negative 5 plus 1 is just equal to 4, well, negative 4. That all over h, so the negative 4 cancels out here. The h's also cancel out. You should do this in a different color, but yeah. The h's also cancel out here, right? Because 1h. And it'll be equal to the limit as h approaching 0 of 4 plus h. And we have our instantaneous rate of change as 4. So that's basically how we can find the derivative of a function at a singular point. So by reviewing everything that we just said, we went over how to find the average rate of change. We went over how to find the instantaneous rate of change using the difference quotient. And overall, we found how to find the derivative of a function. Now, I know it's a really complicated process, but in the next video, we're going to be talking about all of the different rules that we have and for derivatives and how we can figure out how to write them as notation wise. So I'll see you guys in the next video, and always practice these questions. You never know.